Okay, we've talked about acids, talked about bases. Now we're going to get into categories of acids and bases called strong acids and bases and weak acids and bases. The term strong does not refer to the damage you can do to somebody or something if it gets spilled on. It is a chemical reaction that is being described here. So here's the deal with that. If we were to take, say, an example of strong acid, like hydrochloric acid. Hydrochloric acid, when you dissolve it in water, becomes an acid at that point. This is normally hydrogen chloride gas, but when it's bubbled into water, it becomes an aqueous solution. And acids must be aqueous solutions. But because this is a strong acid, this is going to break apart completely when it gets dissolved in water. So we use a single arrow to show that strength. And so it's H positive aqueous and Cl negative aqueous. Now, the single arrow basically says 100% dissociation. Meaning, it breaks apart into ions completely. So if we had X amount of moles here, that is in the solution, there will be none left when you're done with it. If you have 5 moles, you will have no moles. You have 5 moles of hydrogen ions or acid ions and 5 moles of chloride ions, but you will have none here left over. It's all split apart. That is strong. A weak base or a weak anything can do damage to you if it's in concentrated form. Now there's a dilute form where there's lots of water, and there's concentrated form where there's very little water but enough to dissolve everything. Concentrated form can be quite dangerous. It's not a matter of strong or weak, it's a matter of concentration. An example of a weak base is ammonium hydroxide. Now ammonium hydroxide, because it is a weak base, and I'll put aqueous there, because this is dissolved in water. But we use a double arrow this time, and this simply means it's less than 100% dissociated. Now, what that means is it can be anywhere from 0.001% to 99.5% or whatever, or 99.4% that doesn't run off to 100%. But it still breaks apart kind of the same way. Now remember, we're dealing with acids and bases, so one of the ions produced has to be either a hydrogen ion or a hydroxide ion. Well, we got hydroxide ion here, and we tend to put that first just to emphasize the fact that this is a base, and then everything else left over has to be a positive ion because the 2 ions have to add it to 0. So that gives you NH4 positive aqueous. So that's the difference that we're looking at here. Okay, and the whole discussion is based upon the idea of what an acid is, what a base is, and whether it's a strong one or a weak one, for either one. And there's 2 examples of it right there. Now, there is only 7 strong acids: hydrochloric, hydrobromic, hydriodic, nitric, sulfuric, chloric, and perchloric acid. Those are the only ones that are strong. All other acids are weak. So any dissolving of these compounds will be involving a single arrow. The rest of them will have to have a double arrow. Bases, there are 9 strong bases. All the group 1 metal acid, hydroxides rather. Notice hydrogen is not there because hydrogen is not a metal. It is a group 1A, but it's not a metal, so water is not strong. It's very weak, as we have discussed. But these right here are your strong group 1 metal hydroxides, and the bottom half of group 2, strontium, barium, and radium, which have positive 2 charges, so you have to have 2 hydroxides for those, and that makes these very strong. Now, you've been taught that the pH range is from 0 to 14. That is not true at all. Because of the availability of these ions in both strong and concentrated form, you can get anywhere from a -2 to a +16. So if you ever get a negative pH, it's probably going to be right if you did the mathematics correctly. or you just didn't know how to punch it into your calculator. So let's take a look at a couple examples here. Oh, yeah, one more thing I want to talk, that we'll deal with it later. For example here, what is nitrous, what is the formula for nitrous acid and what is the dissolution equation for it? Okay, we talked about how you name acids. If it ends in OUS acid, we said it has to come from the ITE ion. So this comes from the nitrite ion. You look that up in the polyatomic ion chart, and it's NO2 negative. Because it has a -1 charge, it's going to need one hydrogen to neutralize it. So we add one hydrogen to the nitrite, give you HNO2. That is the formula for nitrous acid. That is not one of the 7 acids. Nitric acid, HNO3 is, but nitrous is not. So that means then we're going to use a double arrow in writing the dissolving reaction. So HNO2 aqueous, double arrow, H positive aqueous plus NO2 negative aqueous. And when you take Chem 2, you can learn exactly how much will break down, what percentage breaks down, or what they call the ionization rate. But we're not going to do that here. We're just going to stick with pHs, which we'll talk about in just a little bit. Next one, rubidium hydroxide. What is the formula? What is the dissolution reaction, or the dissolving reaction? Well, rubidium is a metal in group 1A. Hydroxide is a polyatomic ion -1. They already add up to 0, so you just need one of each, so it's RBOH, and that is one of the 9 strong bases I gave you. Therefore, you're going to need a single arrow for this. So RBOH solid, and you don't have to put aqueous in. If you do, it's fine, no big deal. If you do, don't put water above it, okay? So RBOH solid yields with water, rubidium positive ions, and hydroxide ions, okay? The last type of compound I want to look at is the organic base. And remember, we talked about organic bases and how they need to be changed into an Arrhenius base, so we can see the hydroxide and talk about the dissolving or dissolution reactions. So here, how do we know that that's a base? Because we got lots of carbon and hydrogens in them. That's number 1, and that tells you it's organic. And the fact that it's got nitrogen in it, like in this form right here, that makes it a base. And so we call this a Bronsted-Lowry base, because there is no hydroxide, but we know it is a base based upon the identification of that nitrogen. So we have to change it to the Arrhenius base, and as we talked about before, you add water to it in the form of HOH, and so the H attaches to the NH2 to make that NH3, and the OH tags along because it's bonded to it. And so we get this compound right here, CH3, CH2, CH2, NH3OH, also known as propanium hydroxide. But we don't talk about it. We just like to go CH3, CH2. Organic chemists do this, and inorganic chemists hate it, but too bad. Dissolution reaction then, we take this compound, make it aqueous. We know the hydroxide is going to come off to show that it is a base. And then everything else left over stays together as a positive ion. So there's always one negative ion and one positive ion. Okay? All right. So, I believe, yep, that's it right there. So, your practice problems, any minute now. I got the feeling it's going to happen. This is, that was exciting waiting for it like that. So you already give the dissolving reactions for these 5 compounds. I gave you names for 3. I gave you formulas for the other 2. Have fun.